This is the most important lecture of this unit. In the previous lecture, we have seen what are the conditions for ideal MOS capacitor. In this lecture, we will see what happens when an external voltage is applied across ideal MOS capacitor. Our first case is when the gate voltage is negative. In this condition, more number of holes are supplied by the battery to the semiconductor substrate, but since capacitor does not allow flow of current, therefore holes gets accumulated at semiconductor oxide interface. This makes the semiconductor near the oxide interface more p-type. In the energy band diagram, we cannot band Fermi energy level, as band in Fermi energy level means flow of current which is not possible for a capacitor. Conduction band, intrinsic Fermi energy level and valence band of the semiconductor will move parallelly, representing the changes occurred by external negative voltage. In the second unit of p-n junction, we saw any band in intrinsic Fermi energy level represents internal electric field in the direction of increment of energy levels. The similar deviation will occur in oxide. Here also we will have an induced electric field. The electric field direction is quite obvious with the external applied voltage, but there are no bands in metal. This is because of a very important property of metals, that electric field does not exist inside a metal, or in other words, all points within a metal are equipotential. So we can write a very important point, that whatever voltage we are applying, the same potential drop will occur only in oxide and semiconductor. We can also observe that the Fermi level within the semiconductor is not at the same level with the Fermi energy level within the metal. The difference between Fermi energy level within the semiconductor and metal is equal to external applied voltage multiplied by magnitude of charge on an electron. While applying external voltage, the energy bands along with vacuum energy level moves upward or downward. Therefore, there is no effect of voltage on work function and electron affinity. A rough plot can also be drawn representing majority and minority carrier concentration within the semiconductor. Also, mass action law is valid at all points within the semiconductor. These curves introduced within the semiconductor are very important characteristics of MOS capacitor. There are two parameters, Fermi potential and surface potential, which are particularly helpful in MOS capacitor analysis. The Fermi potential is equal to intrinsic Fermi energy level in the bulk semiconductor minus the Fermi energy level in the bulk semiconductor. Bulk here simply refers to the portion of the semiconductor which is deep inside of the semiconductor, such that there are no bands in energy levels. The second parameter, which is surface potential, is defined as the intrinsic Fermi energy level deep inside the semiconductor minus intrinsic Fermi energy level at the semiconductor and oxide interface. Fermi potential is a function of doping. For p-type semiconductor substrate, Fermi potential is positive, whereas for n-type substrate, Fermi potential is negative. Surface potential, on the other hand, is a function of applied voltage and will change if external applied voltage is changed. From the first unit, we have hole concentration to be equal to intrinsic carrier concentration multiplied by exponential of intrinsic Fermi energy level minus Fermi energy level divided by Boltzmann constant into temperature in Kelvin. By rearranging the equation, we will find the formula for Fermi potential. This formula is very important and you should learn it. The application of external applied voltage on MOS capacitor has been categorized into different regions, like the case which we are studying presently is referred as accumulation region. As for the external applied voltage, the majority charge carriers of the semiconductor substrate gets accumulated near the semiconductor oxide interface. For accumulation region, you can see the voltage applied is negative. Similarly, the surface potential in this case is negative. You should remember we have taken ideal MOS capacitor with p-type substrate. If we have taken n-type substrate or we have taken non-ideal MOS capacitor, then the conditions for applied external voltage will change for accumulation region. The second case is when the gate voltage is 0. The surface potential is also equal to 0. For ideal MOS capacitor, energy band within the semiconductor and insulator are straight. This voltage where the energy bands are straight is particularly referred as flat band voltage. For ideal MOS capacitor, flat band voltage is equal to 0. Flat band voltage is a very important parameter whose value does not depend upon whether MOS capacitor uses p-type substrate or n-type substrate, but its value will change if the MOS capacitor is not ideal. The third case is when the gate voltage is greater than 0. In this case, electrons are supplied to the p-type substrate which gets deposited near the surface, resulting in depletion of hole, making it lesser p-type. The Fermi potential will remain the same as it considers only the semiconductor deep inside away from semiconductor oxide interface, and it depends upon the type of doping and its concentration. However, the surface potential in this case will become positive. The case of positive gate voltage is further divided into three parts, which is defined on the basis of surface potential. First is the depletion region. When the surface potential is greater than 0 and smaller than or equal to Fermi potential, then the MOS capacitor is said to be in depletion region. The area within the semiconductor which is depleted of charge carriers is referred as depletion width. In the second unit of p-n junction, we also derived the formula for depletion width. If we assume that we have a one-sided p-n junction, then the space charge width or the depletion width will come out to be equal to under root 2 multiplied by permittivity of the semiconductor into surface potential divided by magnitude of charge on an electron into doping concentration within the bulk semiconductor. The Fermi potential for n-type substrate is negative, so we modify the formula a little bit. The modular sign includes the negative Fermi potential which will be present in n-type substrate. If we have to find the depletion width at the extreme points of the range of depletion region, then we have to put the surface potential equal to Fermi potential. Therefore, by replacing surface potential with Fermi potential, we will get the largest value of depletion width which can be present in depletion region. The minimum value of the external voltage to be in depletion region is 0. We can also find applied external gate voltage at the upper range of the depletion region. We know gate voltage is equal to oxide voltage plus semiconductor voltage. The voltage difference within the semiconductor is Fermi potential, and to find the voltage drop across the oxide, we have the formula capacitance per unit area multiplied by voltage equal to charge per unit area. Capacitance per unit area is equal to permittivity of the oxide divided by width of the oxide, and charge per unit area is equal to magnitude of charge on an electron multiplied by doping concentration multiplied by depletion width. We got this formula by assuming that all the dopant atoms within the depletion region are ionized. The oxide voltage will be equal to magnitude of charge on an electron multiplied by doping concentration into depletion width into width of the oxide divided by permittivity of the oxide. So, after putting the value of oxide voltage and silicon voltage, we can find the value of gate voltage corresponding to the upper range of surface potential. In the second case, the surface potential is greater than Fermi potential and smaller than 2 times of Fermi potential. When the applied external voltage becomes even greater, then the semiconductor near the surface changes its behavior completely, meaning that it behaves like N-type semiconductor rather than P-type semiconductor. This case is referred as inversion region. The last case, when the gate voltage is positive, occurs when surface potential is equal to or greater than 2 times of Fermi potential. If the voltage is even greater, such that the N-type characteristic at the surface is exactly equal to or greater than P-type behavior in the bulk semiconductor, then this condition is referred as strong inversion. This is the most important case, and 70% problems from this unit are asked from this particular case. One special condition is when the surface potential is equal to 2 times of Fermi potential. The external voltage corresponding to this condition is specifically called threshold voltage. This is the most important parameter in the whole chapter. If you understand what is threshold voltage and you can recall the formula for threshold voltage for P-type and N-type MOS capacitor for both ideal and non-ideal cases, then only you should proceed to the next unit, which is MOSFET. Like the calculations we did for the depletion region, the same way we can find the depletion width for strong inversion region as well as threshold voltage, which is the minimum external voltage required for bringing the MOS capacitor into strong inversion region. Very important theoretical point you should keep in mind is that when we applied positive voltage, we got depletion width, and as we keep on increasing the magnitude, then the depletion width rises, but it will rise only until it reaches the strong inversion region. Afterwards, when the voltage exceeds threshold voltage, the depletion width remains approximately the same. However, the accumulated charge near the interface increases significantly. I hope you have understood this lecture very well, because if you have clearly understood this lecture, then the whole chapter is a piece of cake for you. It is good for you if you think that you have understood this lecture, but to certify that, I recommend you to derive all the relations, formulas as well as parameters for MOS capacitor with N-type substrate. Firstly, you should keep in mind the verbal definition for different regions. Depending on that definition, try to visualize what should be the condition for surface potential, and finally, depending on surface potential, try to define the condition for applied external gate voltage. Short notes are attached in the video description. The last link is of the current unit, and rest of the links are the short notes for the previous unit. So, click on the last link and check the relations which you have derived for N-type MOS capacitor. Don't get confused by the symbols E and Q, as sometimes I have used the symbol E and in the short notes I have mostly used the symbol Q, but both these parameters represent exactly the same thing, which is magnitude of charge on an electron.